I'll sort it out. Get paid for that. You don't. So much money. Okay, and so I had one student last year, last semester, in honor of the James Bond movie that came out. He sent me this, so Matt, last name. Look. Sophomore. Brightman. Yeah, thank you. I was like, gosh, his last name. So we're like, bond, ionic bond, taken, not shared. Okay, so ozone, you're starting here, and then we're going to go to ethene. We'll talk about how to name these next week, and then we'll go to sulfate. So what's your very first step in every single type of fluid stop? Count. What are we counting? Valence electrons. Okay, so we are teaching James today, guys. Okay, we have to make sure we talk through the steps of how to do a Lewis dot model. So count them up. Got your PTO video? We are moving. So 6 plus 6 plus 6 from each of these oxygens gives us 18 valence electrons. Go ahead and count this up too while we're here. So carbon carries how many each? 4 each. So that's 4 and 4. That's 8 so far. Plus how many does each hydrogen carry? 1 because it's in group 1. So 4 plus 4 plus 4. 12 valence electrons on this one. And then sulfate. So so sulfur carries how many?
6.
6 because it's in group 6. Plus 4 oxygens each carrying another 6, right? So yeah, that's 24 together. Then we have this weird thing here. We have a charge on the outside. That -2, what does that mean about the overall molecule? It has 2 more electrons than it should. So how do I indicate that here? I actually add 2 more electrons to my net because it needs to indicate, it needs to agree with the charges here. So we have 24, 32, 32. Ooh, electrons. Valence electrons. Okay, so let's start with ozone. Just I want to make sure we're clear the group number is the valence number. Okay, so ozone is first. How do you want to organize it? So we got our valence counted. What's the next step? S means skeleton, right? So who goes in the middle? Take a pick, guys. Can't get it wrong. Let's choose oxygen. Okay, if you chose something else, you're wrong. Just make that loud and clear. And we put oxygens on either side. And then I need to now do what? So add everybody up to octet, right? So let's just throw those electrons on there to meet octet, and then we can adjust if needed. So I saved these for today so we can adjust as needed. So octet, 2, 4, 6, 8. 2, 4, 6, 8. Okay, so that one's good. 2, 4, 6, 8. So everybody's surrounded by octet, right? So how many electrons are on our structure? We're reviewing it right now. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Oh no. Okay, so what do we need to do? How many do we need to erase? Because we only need 18, right? So what am I going to force it to do? Share. So what you do is you erase 2 lone pairs, 2 sets of lone pairs. I'm just going to erase it from my left one. Oh, sorry, my right one, your left. What's your left one? Okay, your right one. Okay. And then the one in the middle. So instead of letting them each have an individual lone pair, you're like, hey guys, you're going to have to share. Boom. Double bond. Okay, so now we double check. 2, 4, 6, 8, 10, 12, 14, 16, 18. Yay! What else could I have equally done that makes almost exactly the same molecule? I chose to erase lone pairs from the central and the right one. Maybe what could you have chosen to do? That's equally acceptable. Yeah, just mirroring it, right? So you could have written it out like this. Okay, so It's basically the mirror image of this, right? So I chose for the double bond on the right side, and then we're like, hey, this is equally acceptable, double bond on the left side. It does not matter. This has a special name. If you can draw two valid Lewis structures, they are called resonance structures. Did you see that in your book in reading at 8? Resonance structures. Okay, so that's a good term to know. And the way that you say, hey, these are equally acceptable is you put a big bracket around both of them together like this, and then you draw a little arrow between them like this to say it's either one of these are acceptable. And that's how you kind of indicate the entire thing is very correct or valid. Okay, so know that. Cool. You drawn this. We're moving on. C2H4. Okay, C2H4. Ooh, oh, sorry. A little sheet that I not access to you. Tell me what the shape is of this ozone molecule. Okay. That's fine. I can go here. Just first. And then these are just big sheets. Whatever's extra, just put in the bottom. Okay. What is the shape of this ozone molecule? We gotta look at the lone pairs. You gotta look at the ligands. So let's count these out loud. We gotta help James, okay? Looking at the central atom, how many lone pairs? One lone pair. Okay, looking at the central atom, how many ligands? 2 attach. So a ligand is an atomic attachment. There's one ligand here, and there's one ligand here. Do not look at the actual bond type, double, triple, or single. Look at the attachment. So there's a ligand and a ligand. So there's 2 ligands. Is there a shape on there for you? Bent. Yes, that is a bent shape. So what you can see by these structures. This is an elephant. That is not. It's benzene. Hold on. Okay, so that's what it looks like. There's a lone pair sitting up here. What is that lone pair doing to these bonding pairs right here? Right, they're being bullies, and so normally you're like, hey, you know, we drew it linear. I can draw it look like a dinosaur. It's not a dinosaur. You can draw it however you want, but you have to think about spatially how does it reorganize itself. We draw it like this, but we know that lone pair on the top of the blue pushes those away from each other to make it repel, to make it out of the bent shape. And that's why you have that cheat sheet to help you kind of reason with yourself. You're like, I drew it linear, but it's not. It's actually bent. So the resonance structure is the same over here. It's also bent. All right, let's do the C2H4. So you guys have 12 electrons to work with here. Okay. So what do you guys want to choose for your skeleton? How do you want to lay it out? How do you want to lay it out? What's going to go in the middle? Okay, how about both carbons? Can we make it look like a carbon chain? So maybe a carbon attached to a carbon? And then what are you going to do? Right, 2 hydrogens on each side, because we want to make it as symmetrically as possible because it will help with the stabilization of the molecule. Okay, so now we've got how many electrons taken care of? Remember, we only have 12 to work with here. So 2, 4, 6, 8, 10. 10. All right, who is happy as can be? Hydrogens, because it's not able to accommodate octet. It's just too small. We've got 2 electrons there, 2 electrons here, 2 electrons here, 2 electrons here. We're good. Who is not happy? Either carbon. So how can I make them both happy at the same time? A double bond. Boom, right there. So you put the double bond there to satisfy octet, and it only gets us up to 12, and then we're good. This one does not have a central molecule, so we're not going to do the shape for it because there's 2 centrals, so that's more difficult. Okay, this is an organic structure called ethane. Have you heard of ethane? Ethanol. It's just a version of that without the oxygen. The last one is SO4 2-. So we had what, 32 electrons to work with here? Skeleton, what you gonna put in the middle? S, and then 4 oxygens, okay, symmetrically as possible, so put the O's on the outside. Okay, so what do you want to do next? Give everybody octet. Okay, so let's just see how that works. So you're putting 6 more electrons around each of the oxygen. I thought I heard somebody. What's password? Hi, Eli. Come on in. There's no password for you. Okay, so we put 8 around each of them. How many total are on the structure? There are 32. Now, this one is going to actually need to be changed a little bit, and this is a more advanced concept, but we're going to try it to make it more stable. And I won't tell you everything right now because you want your minds to stay the way they are. I'm actually going to show you something called expanded octet. I'm erasing 2 of these lone pairs on the outside of the oxygen, and I chose the left and right one. I could have equally chosen the top and bottom one. You should start taking notes with us now. So, and I'm going to add a double bond there. To replace that lone pair, I just smushed it to the middle. I took that lone pair and pushed it to the middle. So, we have a special case here. How many electrons are around sulfur? 10. 2, 4, 6, 8, 10, 12. Sorry, 2, 4, 6, 8, 10, 12. There are 12 electrons around sulfur. Is that allowed? Technically, octet is a guideline. Most things will do octet, except for hydrogen, right? And then there's like beryllium. So I'm going to point up to the periodic table for you. Beryllium and boron are also super tiny. So hydrogen's tiny and only gets duet. Beryllium and boron are also small. You might see them have under octet. I'll do an example with you in a second. And then you get over here. Carbon's always going to have octet. Nitrogen's always octet. Oxygen's always octet. Fluoride's always. Neon doesn't bond, right? Then we have this little second row down here. What period is this? Third period. Where does D block come in? What energy level? The third. Remember when you go, okay, 3b6, 4s2, 3d10. Technically, this phosphorus, sulfur, chlorine, and argon, if they wanted to, they have a third energy level, which contains the accessibility to D block. So I will think of D block as 5 extra pockets, because there's 5 orbitals, right? D block in the third energy level allows sulfur to expand its octet, has extra pockets for these electrons, and we'll see that a couple times today. So this is expanded octet, and it's only for anything in the third period, aka third energy level, right? Because that's where D block is now initiating. That's where it's starting to come in. Third period, because 3d electrons are orbitals or pockets. 3d orbitals. And they allow those extra electrons to have a place to stay. So we're going to draw some more like that. There's one more part of this. You see this -2 charge? We got to account for it. So that's got to be here. And the way we do it is we put a big bracket around the entire structure, like that. And you just put a -2 charge on the outside to indicate that that whole shebang's got a -2 charge. So those were a little bit more complex than yesterday's. So maybe that helps with some of your questions you may have on your structures you drew last night. Maybe. Because you probably are like, I've got so many electrons, what do I do with them? On some of those bigger ones. So we'll talk about those as we go. We're going to finish up molecular polarity, and then we're going to allow you to build these, look at them, talk about everything we possibly can talk about for these molecules, except for one thing, IMS, which we'll do next week. So this will make a lot more sense. The molecular polarity, I'm going to talk about it. You're going to be like, I'm a little confused. But when you build them, you can see it better. Okay, so listen to me now. Take notes, write them down, and then we're going to jump on molecular polarity. I'm going to show you a video first that actually give you some more insight on what these molecules are doing with each other. So, not that video. This video. So I want you to write down one thing you learned from this. Just one. Just one. Let me pause this. I can change it up.
What is the shape of a molecule? Well, a molecule is mostly empty space. Almost all of its mass is concentrated in the extremely dense nuclei of its atoms. And its electrons, which determine how the atoms are bonded to each other, are more like clouds of negative charge than individual discrete particles. So a molecule doesn't have a shape in the same way that, for example, a statue has a shape. But for every molecule, there's at least one way to arrange the nuclei and electrons so as to maximize the attraction of opposite charges and minimize the repulsion of like charges. Now let's assume that the only electrons that matter to a molecule's shape are the outermost ones from each participating atom. And let's also assume that the electron clouds in between atoms, in other words, a molecule's bonds, are shaped kind of like sausages. Remember that nuclei are positively charged, and electrons are negatively charged. And if all of a molecule's nuclei were bunched up together, or all of its electrons were bunched up together, they would just repel each other and fly apart, and that doesn't help anyone. In 1776, Alessandro Volta, decades before he would eventually invent batteries, discovered methane. Now, the chemical formula of methane is CH4. And this formula tells us that every molecule of methane is made up of 1 carbon and 4 hydrogen atoms. But it doesn't tell us what's bonded to what, or how the atoms are arranged in 3D space. From their electronic configurations, we know that carbon can bond with up to 4 other atoms, and that each hydrogen can only bond with 1 other atom. So, we can guess that the carbon should be the central atom, bonded to all the hydrogens. Now, each bond represents the sharing of 2 electrons, and we draw each shared pair of electrons as a line. So now we have a flat representation of this molecule. But how would it look in 3 dimensions? We can reasonably say that because each of these bonds is a region of negative electric charge and like charges repel each other, the most favorable configuration of atoms would maximize the distance between bonds. And to get all the bonds as far away from each other as possible, the optimal shape is this. This is called a tetrahedron. Now, depending on the different atoms involved, you can actually get lots of different shapes. Ammonia, or NH3, is shaped like a pyramid. Carbon dioxide, or CO2, is a straight line. Water, H2O, is bent, like your elbow would be bent. And chlorine trifluoride, or ClF3, is shaped like the letter T. Remember that what we've been doing here is expanding on our model of atoms and electrons to build up to 3D shapes. We'd have to do experiments to figure out if these molecules actually do have the shapes we predict. Spoiler alert, most of them do, but some of them don't. Now, shapes get more complicated as you increase the number of atoms. All the examples we just talked about had one obviously central atom, but most molecules, from relatively small pharmaceuticals all the way up to long polymers like DNA or proteins, don't. The key thing to remember is that bonded atoms will arrange themselves to maximize the attraction between opposite charges and minimize the repulsion between like charges. Some molecules even have 2 or more stable arrangements of atoms, and we can actually get really cool chemistry from the switches between those configurations, even when the composition of that molecule, that's to say the number and identity of its atoms, has not changed at all.
All right, so he mentioned the whole, they arrange themselves to limit the repulsion. There's a big word for that. It's a theory. It starts with a V. Say again? VSEPR theory. Why do you think I made up that acronym to match our process of doing our Lewis cost structure? So we actually would remember what the heck VSEPR theory was, and specifically what it's supposed to be describing. Oh, before I jump on VSEPR, here's my cartoons for you. Which one is nonpolar covalent? So the left picture, the right picture. Raise your hand. With your right hand, you say the right picture, and your left hand, you say left picture. Okay, I'm feeling some rights. Okay, so why is this describing a nonpolar covalent bond? Right, they're like, all right, they're equal sharing. There's no side left or right that has more electron charge or electronic charge than the other. So this one's definitely the polar covalent. So which side is more negative? So hydrogen side or chlorine side? Chlorine side. And why is chlorine going to be pulling the electrons towards itself? Because it's about that trend. Right, it's higher in electronegativity, so it pulls the electrons towards it. This one's lower in electronegativity, so it allows electrons to be pulled away. So that's going to be playing into us in terms of our molecular polarity in a second. All right, here is that VSEPR theory. I think the video did a great job of helping you understand what it is, but write down something for yourself to represent what it means. And it is specifically, you should know what it stands for. Valence, shell, electron, pair, repulsion. Valence shell, electron pair, repulsion. That's exactly what we've been kind of saying, but we actually have a term for it now. And actually, we've been using it. You guys have been using this the whole time actually to predict the shape, these molecular geometries, and you didn't know it. And that's why, I mean, I wanted to show it to you first because it makes a lot of sense, but then here's some of the theory behind it so that you have some context to it. So it helps us predict that 3D shape of the molecule that we've been using since yesterday. And so there's all those different shapes: tetrahedral, trigonal, pyramidal, bent, linear. We're going to start to see some trigonal bipyramidals and octahedrons. We're going to see a lot of stuff in the lab. And the premise behind it is simply electrons repel, they like to spread out, and it makes this shape after they do that. So that's what some of this is talking about. The electron pairs are going to repel to affect the shape of the molecule. And we're always really focusing and honing in on the central atom to see how the atoms and ligands arrange themselves around the central. So, like, I don't believe any of this is really new. So we're looking at lone pair, we're looking at the central atom, we're looking at ligands all together to determine the shape. The only new thing is that I'm now mentioning this term bond angle. And I did mention bond angle yesterday for tetrahedron. What was that bond angle? 109.5, right. And actually, this is going to change a little bit every time we add more lone pairs. But as lone pairs, they're pushing and they're repelling. So every time I add a lone pair, actually to a tetrahedron, it actually goes down just a tiny bit because it's pushing the angle together. These are actually things that we just learned in AP. You need to know the tetrahedron is 109.5. You just need to know the other ones are lower. You don't have to know these exact numbers. But, you know, if you plan on taking AP, you're going to learn it this time this year. So basically, as the lone pairs come together, it's just pushing this bond angle together more and more every time, just because they're repulsive. So let's do one more thing. Let's look at molecular polarity. What was the polarity thing we talked about yesterday? Was it about the molecule or was it about the bond? Yeah, 50-50 here. Take a chance. Bond polarity. Yesterday we talked about, we already did the resonance, okay. I'll come back to this expanded octet in a second. Let me get here. Okay. Yes, we're going to talk about this right now. Yesterday we talked about 3 types of bonds: ionic, non-polar covalent, and polar covalent. And we used that electronegativity chart and we looked at the differences in numbers. And we said, okay, it falls in this range, or this range. That is called bond polarity. Do not confuse that with molecular polarity, which is what we're doing right now. I'm going to let you read and write because this is the longest slide. This is our last slide for now. This is the guts of today. I know you've heard of molecules being polar before. What is the best known molecule that is polar? Water. Who's heard that water is polar before? I think I've actually asked this before. Okay, so an example of that is something that you know, water. And I'm going to help you see why it's polar from a 2-dimensional standpoint, and then we'll see it in the lab from a 3-dimensional standpoint. Where are we? Are we down to bond polarity? Almost. Okay, I'm going to scroll down just a little bit. I'll scroll back down. I'm going to start at the top and then talk about some of these, and then we'll get back down here in just a second. Okay, so now that we actually know a bit more about the bond polarity being polar covalent, non-polar covalent, or ionic, ionic is actually not really in this discussion at all, because do you guys know what molecular is referring to? What kind of bond is it referring to? Ionic or covalent? Covalent, right. This is only talking about covalent molecules, not ionic compounds. So we're only sticking with things that are sharing electrons at this point. So I'm actually going to even scratch that out, because that's not an option for us right now. It is in the in our lab, but not right now. So we have to consider the bond polarity, the shape, meaning the geometry, and that from those two standpoints, that's how we make the decision: is this molecule polar? Is this molecule not polar? So I'm going to show you the picture of water first. So water, this is what water looks like. What is the red one representing? What element? We got H's and O's, people. Which one? So what's the formula for water? H2O. I want you to tell me which one's the red one. The O, it's the one that's a single, okay? And then these two are the H's. I guarantee you almost half the class will draw it wrong on the test. Draw it H2O, okay? Not two O's and H. So what we have here is that hydrogen and hydrogen are pushing their electrons towards oxygen. Why? I'm going to draw this picture. It's a good representation. Why is it pushing the electrons towards oxygen? There's a reason. Because with a trend. What trend? Scott? Close, but no cigar. What is the trend that we have on this nice little chart in front of us? Electronegativity. Okay. The oxygen's electronegativity is like a 3, 3.5. What's the sound yours? 3.5. Okay. And hydrogens are 2.1 or 2.2. Regardless, it's very polar covalent bond. Okay, so a PC, polar covalent bond. So that's why I'm pointing the dipoles towards from hydrogen to oxygen, from hydrogen to oxygen. So then we also have this lone pair here. You can't see it on this drawing, I'm going to draw them for you. There are two big lone pairs. Those lone pairs are because the entire H2O molecule is 8 electrons total, so that's 2, 4, 6, 8. So in this case, these lone pairs are very negative, right? And then you've got on top of that, you've got a pushing of electrons to the left side. So what would you say generally the charges of the left side of the molecule? Say again? Probably very negative. So this whole hemisphere is basically negative or partially negative, as you can see in this little partial here. So then what would you say about the right-hand side of the molecule? Right, they're lacking electrons, right? So they're pushing the electrons that way. So this is partially positive. So what we did was we considered the bond polarities and the molecular shape being bent. And we said this molecule has a left and right hemisphere which have two different charges. So unequal distribution of electrons, polar or nonpolar? Say again? So unequal distribution of electrons. Polar, right. Think north and south pole. Unequal, right? Not the same. Polar, north and south pole. Water is polar. Unequal distribution of electrons means polar. So this is a polar molecule. So our two distinctions are polar molecule or nonpolar molecule. That's of molecular polarity. Of the bond polarity, we said nonpolar covalent and polar covalent. So when you say the word covalent, you're talking about a bond. If you don't say the word covalent, I'm assuming you're talking about the whole shebang, the molecule. So that's not very different, so you got to be careful with how you say it. But then, of course, you know, help, I'm dissolving, because polar and polar, they dissolve in each other. So polar, oh, dissolving. The other one's like, no, you're not. So it's easy for you to say you're not polar. Okay, guys, thanks for supporting my comedic career. So bond polarities, if the bonds are nonpolar covalent, there is no way this thing's going to be polar. Okay, if the bonds are nonpolar covalent, just say it is nonpolar, the entire molecule. If the bonds are polar, you have to look at the shape and see if the shape allows for cancellation. For example, one of the molecules you drew on your sheet was carbon dioxide, right? On your lab sheet, carbon dioxide, CO2. Yes, let me review that real fast with you. Carbon dioxide says CO2, how many electrons? So 6 plus 6 is 12 plus 4, 16. Okay, you drew carbon dioxide. You should have drawn it similar to this. Because if you had given everybody octet, you'd have had 20 electrons on your structure, and we need to drop it down, so we force them to share. Okay, and I think we actually drew part of this yesterday. So in this example, this is a 2 point, no, we said oxygen was a 3.5, I think. Oxygen's a 3.5, and carbon is a 2.5, yeah? So the dipoles point from carbon to oxygen, from carbon to oxygen. So the dipoles are showing that the left and right side of a partial negative and a partial negative. What shape is this? So I've drawn it linear. Double check. How many lone pairs on the carbon? How many lone pairs on the carbon? Lone pairs on the carbon. 0. Right. There are no, on carbon, there are 0 lone pairs. So 0 lone pairs. How many ligands on the carbon? 2. This is one ligand over here, and this is one ligand over here. So what shape is that? Linear. It's linear. Okay. So there are 2 ligands. So yes, this is a linear molecule. So what happens here is the linearity of it allows it's like a pulling this way and a pulling this way. Does anybody win that tug of war? No. So it's equal on the both sides, equal distribution. What would you say? Polar or nonpolar molecule? Nonpolar, right. Equal distribution of it would be a nonpolar molecule. Okay. So look at your lab sheet. Notice what the next columns are that you're going to be filling out. What's next? So shape, what else? So molecular polarity, right? Lone pairs and such. So you guys are going to be building these. I'll give you a couple of hints for class before you go back. Each of the sets have like a little card in there that tells you which the atom colors are probably which of the actual elements. So carbon is a black one, oxygens are red ones, hydrogens are white ones, nitrogens are blue ones. They'll have that because it'll help you find the one with the correct number of holes on it. Because what you're going to have to do is leave room for a single bond if you need a single bond. A double bond requires you to use these little flexible. You see that these have like they flex. Okay, that's what a double bond looks like on these structures. So you just have to make sure you have enough holes on the little beads so that you can actually make it look like it's supposed to look. If you have a lone pair, you just leave the hole open like that. That would say a lone pair. Okay, so you'll be working with a partner. I have 12 sets from. I think I have 12 sets. I might need a couple of groups of 3. So be sure that you do not lose these things. And what you'll do is you will build one, raise your hand, maybe let's say build 2 or 3, raise your hand, I'll come check them off to make sure we're good, and then you'll deassemble and keep moving on. Okay? So let's partner and triple up and then get going. Okay? Bring your stuff back there. I'm going to watch and make sure that you have your models drawn. If not, you cannot build until your models are drawn. That is the rule.